in the causality chapter. Has anybody got any questions? I cannot hear you, so you need to type basically. If you have any questions, just say stop a moment in the chat and I will try and answer. Okay, I will pause. Well, let's go through the first exercise until then. Right. So have some actions. And some outcomes. And what we would like to do is maximize our expected utility, and the utility in this case is just equal to the outcome. Okay. I think in all of these problems the actions are binary and the outcomes are real numbers. Okay, so what does the first exercise say? Well, it says that the data we have generated are from some policy pi 0. So that 80 is sampled from some policy pi 0 in a random way, and that yt given the value of AT is drawn from some normal distribution with parameter A plus theta, okay, and variance 1. Okay, so in the first assumption we can say that P0 is just Bernoulli because the action only has 2 values, so P0 is the parameter of the Bernoulli distribution. Okay. Now, what do you think is the distribution of yt if we know pi 0 and theta? Any guess? Recall that when pi 0 selects action 1, then we sample from theta plus 1, and when pi 0 selects action 0, then we sample from the normal distribution with mean theta, right? So that looks like we are sampling from a mixture of Gaussians. Okay, so it's basically going to be pi 0 so that's a standard way of writing a mixture of distributions. Yeah. So let's check it out. Yeah. Okay. So let's do it here. We already have something working. Make this font a bit bigger. Okay. Okay, so let's recall this exercise. Let's use the same So what we want is a way to sample from the distribution. Fine. So let's say we have a class, basic policy. Okay, and we can initialize it with pi. That's it. And then we have sample action. Okay. We can make, because later we will use this. Let us say that pi. How do you do this? NP random choice, I think, is the right form, but let's check it out. Let's put this here. Okay, and NP random choice. How does it work? There is. Okay. Yeah, that's what we want, right? So we have just two choices. We want one sample, and pi is going to be 1 minus pi and pi. Okay. So that should give us a random actions. And then let's start Python. Fine. Just this should work. Just copy pasting. Okay. Right. So let's say policy is basic policy 0.1. Okay, and then we'll say policy get action. Oops. This is a stroke wrong here. Let's redefine the policy. Oh, come on. What's wrong here? Oops. Policy 0.1, and then we just need to get the action. Okay, so let's say A is just action, it's nothing. Yeah, I have to return it actually. How do we import a model? Model in Python. There is reload. Okay, fine. Reload exercise. Okay, this has to be defined somewhere. Where is it? Import lib. Import lib. Okay, great. So now doesn't work. I have to do it again. Policies. Exercise again. Da, 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 da. Okay, and then policy action. Yeah. Great, finally got it working. It's a bit of white noise, you say. Okay, let me check the microphones. This is the closest microphone to one place anyway. And I have another microphone. Is this microphone better? 1, 2, 1, 2. I can turn off both microphones. Tell me if it's better when you have both microphones on. Is one of them slightly different than the other? Yeah. Okay. Right. So okay, so this is simple enough, right? So now we just want to plot the normal distribution for these two things. So let's just put it here actually. Policy is basic policy 1, and now we want to do this for a number of samples. Let's say so let's actually just do the same thing here ourselves. Okay. So we have to find a model, and let's just make a basic model here. I'm doing this just so that we have the same interface for everything. Okay, so here I just want to make, let's say, well, self mean is equal to mean, and then def get response, self action, return np random normal, and action plus mean and 1. Size is 1. Okay. Okay. So that should work. Too many indices for array. Why? Let's do this first. It's defined. That's fine. Okay. I didn't import one. Fine. And why doesn't this work? Too many indices for array. That's strange. That's how to do it. Something like this here, right? La 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 la. Okay, p array 1 is different. It just has one number, 1000, is that what it means? No, that's a different thing. That's weird. Count as array. An array, object, size. Ah, yeah, that's how 0. That's how we do it. Okay. That's fine. Let's define the model. Model is basic model. Okay. Get response. What is that? Now that is very weird here, because get response is the same thing as there, and it's defined. Okay, fine, that works. Great. Okay, so now let's plot the means. There's this nice plot, I'm busy right now. I'm busy right now.
Okay.
Okay, das ist as this plot y. Okay, so this should work, I guess. Let's see. That's okay. Right. So this looks kind of like a single normal distribution, which is kind of acceptable because here we have basically most of the time one thing. So it should be action mean. That's weird. Small thing here. Yeah, okay, now it's a bit clear. Okay. So okay. So this is a mixture of Gaussians. It doesn't look very much like it, but it is. And there is one peak around 10 and one around 11. So you need many more samples to see that there is actually a difference. If we reduce the variance a little bit, then it will be obvious that there's a difference. Yeah. Okay, that's more obvious. So let's make it 0.5 kind of make a proper mixture. Okay, so we have a mixture of Gaussians, and this mixture has been generated by the fact that we have this policy that sometimes takes one action, sometimes takes the other action. Okay, so this is fine. Now what we need to do, we need to estimate theta, right? And what we know about the model is that theta is such that, let's see if this work. Yeah, we know that theta is such that in fact what we observe depends on a plus theta, right? So we can do a small trick here for estimating theta. Can someone guess what the trick is? So we know that the value of y, so we know that yt is equal to at plus theta. Okay, so it means that theta is always yt minus at. Okay, so in this simple scenario we can basically have an estimate of theta which is just the average yt minus at. Okay, so let us say hat theta plus equal yt minus at. And then hat theta is equal to 10 samples. All right, and now we have an estimate for theta. Okay, so let's say this part, get an estimate for theta for a simple model where the response is an additive function, an expectation of theta and the action. All right. Now, this is basically the maximum likelihood estimate of theta, because it gives us well, the empirical mean of a Gaussian distribution is the maximum likelihood parameter. Yeah. Now, if you have time, you can play later with it and find the posterior distribution for a normal prior theta. This is given so well, actually, so if you look at this Wikipedia page, it tells you what is the prior distribution you can define for a mean, for a normal distribution with a known mean. Okay? So if you have a normal distribution with known variance, sigma squared, in this case let's say 1, then you can define a prior over the parameters, in this case the mean, in terms of a normal distribution as well. And this normal distribution will have prior parameters mu 0 and sigma 0. Merely specify your uncertainty about the mean of the normal distribution that you actually observe. And the posterior hyperparameters are quite simple. So one of them is basically the empirical mean, yeah, regulated by the variance that you observe. Okay. And the other is basically a mixture between your original variance, sigma 0, and the empirical variance that you observe. Well, you know the variance anyway. Okay, so it's possible if you want to play with this and get the posterior distribution for the mean. Okay, now this is fine. Nothing special about that. Just for the estimation. Now what you would like to do is plot the mean variance as pi changes. Okay, so basically if we do this now, we'll actually get the variance will not change because the variance of the model is 0.5 anyway. The mean will always change to be just proportional to the action that we take, proportional to the probability with which we take action 1 versus action 0. So the only thing that will change basically is how much each of these individual Gaussian distributions is weighted, right? So for one case it will be like this. What happened here? Here. No. So when pi is small, then the average will be closer to 10, because here this is where very little, and then when pi goes closer to 1, then the average, the mean goes closer to 11. Yeah? So that's the basic idea here. Now, this is nice because for causal problems this is kind of nice. Can somebody think about why it's a nice property to have for causal models? To have this kind of structure, where the response is basically a sum of the action and the unknown parameter. Because of the model structure, right? No matter what action we take, we still estimate the theta parameter with the same rate. So we still have the same number of samples for the theta parameter. So we can always take one action, action 0, and still estimate theta. We don't have to play different actions to estimate the theta. It's different for the other model. Okay. So now let's say for the model where the response depends is one of two different normal distributions. whose mean arbitrarily depends on theta, okay? On action, sorry. So before, what we did was that the action tells us that the mean is now the action plus the original mean, but now for the let's say the standard model, let's call it the standard model, we basically have this, okay? So now the mean is a vector, okay? So now we can try and plot it again. Okay, so we have 10,000 samples again. This will have this one. We have to select something for this, and let's say that one mean is at 10, okay, and the other mean is at 11. Okay, but we don't know if what it's one is. So it could be like one is at 3 and the other is at 11, or one is at 9 and the other is at 10. We don't know really these means, okay? Could be any arbitrary means. Okay, so now we can also run this one, and this one now has to be an estimate for two parameters, right? Because there are two means, two Gaussians with two means. There are no relations between them that we know, so we'll just say the vector of size 2, okay? And just to make it a bit more okay, so let's see, I don't remember how it works exactly, so let's see, NP random uniform, yeah, that's fine. So let's get a completely random vector here. I don't really know what the means are going to be. I'll just take it, make it normal even just a minute. Yeah. So I have some random name for the normal, and we have 10,000 samples from it. And again, the original estimate is this one, right? And we know from the model that whenever we take an action, then we get a sample from the corresponding Gaussian distribution. For action 0, we get something from 1, and for the other one, we get from the other. Right? So if we just write it, we just have yt given at, and theta comes from a normal distribution with parameter theta at and some variance, let's say 1. Doesn't have to be 1. Okay, so now we have two different parameters to select, to estimate, and because we take, if we always take the same action, then we'll only estimate one parameter. Okay. Okay, so that means that we must calculate theta hat I to be sum of a number of times we have selected so here we just count the times where at is equal to I, and then we divide by the number of times that at is equal to I. Yeah. So in code it's pretty simple as well. Okay, so counts 80 plus equal 1, and then what else? Hat theta plus hat theta 80 plus equal 20. Okay, and then you say hat theta divided, so I don't know if it works, but let's try it. That's the first figure. Second figure doesn't work. Why? Setting an array element with a sequence. It's nothing different. Okay, so 80 equal 1. So what is this? Okay, so this response is a vector for some reason. Fine. Why is the vector? Let's see. Self mean equal mean and random normal self mean action. What does this mean? Huh? Didn't even try to do something? Am I using the wrong model? Ah, yeah, that's possible. Basic model, fine, yes. Standard model, yes, thank you. Just complain about something. Using a non-integer number instead of an integer will spend. Fine, what's the problem here? So action is 1 and this one. Fine. That's fine. Should work. I don't know what the problem is here. Why is it complaining? Let's say 1. Let's complain about this as well. That was weird. Okay, so hat theta is this one, and let's assume that these are the same as the means. Yeah, these are the same as the means there, right? Okay, so we can estimate. I mean, the problem is that if we are taking an action very few times, so let's say we only take, let's take fewer samples and see what happens. Yeah. So now this one is well estimated probably, but this one is not. Because here we only take this 100th of the time. So while we have 1,000 samples, for that one we only have 10, and for that around 900, right? right? So that means that our estimate for that one is not so good. But we do have an unbiased estimate of this. Okay? So that's not too complicated either. Just estimating the models themselves. Okay. Now, for the second part, we didn't do this estimating pi 0, but if you need to estimate pi 0, it's not very difficult, right? We can do it here as well. Hat pi policy is NP zeros. There are only two actions, and you can say policy AT plus 1. You can say policy so you can get this as well if you wish. Okay, so the policy that we estimate is pretty close to the one that is actually there. Okay, it's a bit harder if your policies depends in a complicated way on observations. So here, so far, we've been only dealing with a fixed policy that only takes the same action probabilities irrespective of any observations. And we generally have some policy that depends on some observations, right? And this makes things a bit more difficult. Especially if you don't really know the policy, because then estimating it is another additional problem to just estimating the distribution of outcomes depending on the actions. So if you remember what we had here, the general structure is that okay, let's go here. Let's go to the general structure here instead. Okay. But the action depends on some observations and on what the policy parameter, and the outcome depends on both the unknown parameter, the observations, and the action taken. Okay, so far we didn't have this x, so it was quite simple. But if you have the x, then you can imagine that maybe the policy maker, decision maker, takes a different action for every different x, or uses different action probabilities for every value of x. So if you can think about this as a standard machine learning problem, estimating this action probability given the x is like a classification problem, okay? Where basically the classifier you're trying to find is trying to match this policy, okay? And here, what you're also trying to learn as well is what's the probability of y given x and a. So if y is a discrete variable, then you can think of this as another classification problem where we're trying to learn this parameter here, okay? But this is only half of the problem, because just estimating this existing pi and estimating this existing theta is fine. In the end, what you want to do is finding the optimal pi, given what you know about theta, okay? And there are two ways to do this. One is to build a model. So directly estimate theta, estimate the other pi if you need to, but mainly estimate theta and then find the optimal pi. And the other way to do it is to use importance sampling. So let's take a short break, and I don't know what will happen to the stream if I stop it. Will it be the same stream or will it be another stream? But I will stop it and see if it's another stream later. Okay, so see you around 10 past 11.